we've dealt with all the situations where pressures changes and volumes change and temperatures change. And first we kept two constant, right? The number of moles and pressure, or number of moles and volume. We kept two of them constant. That made the equations really simple. Then we said, what happens if you just keep the number of moles inside constant? Then we got combined gas law yesterday. So the fourth part that changes is the moles. And we already know how moles are related to stuff. We learned it in the past. That was Avogadro's hypothesis, which was that the volume is proportional to the number of molecules at constant temperature and pressure. This is where we got the fact that 22.42 liters is 1 mole at STP. I picked a temperature and a pressure, 0 degrees Celsius, 1 atmosphere, and I found out that 1 mole was 22.42 liters. So as I put in more molecules of gas, it's going to take a bigger container for them to hit just as hard. Because if I leave them the same size container, they'd hit harder. They'd hit more often, right? So if I want the same pressure, I'm going to need a bigger container if I put in more gas molecules. Is that logical? Okay. So volume is proportional to the number of moles. And I didn't say what kind of proportion. So when scientists leave off the type direct or inverse, they leave it off. It's assumed to be direct. Direct is the default position. So if somebody says it's proportional, it's directly proportional. If it's inversely proportional, they always say inversely proportional. Okay. So V equals K times N, where N is our symbol. The only thing really new here is N is the symbol for moles. And they picked N because moles is a number of pieces. It would work in dozens too. It would work in scores, but those numbers are too small. We need Avogadro's number to get reasonable. Okay, and we could solve for K, V1 over N1 equals V2 over N2, but nobody ever does that. Okay. What they do is I got to put N into the combined gas law. So all I really have to decide is N going to go on the top or on the bottom of the combined gas law? Well, it's directly proportional to volume. What else is directly proportional to volume? Temperature is directly proportional to volume, so V needs to go where, or N needs to go where T went. Does that make sense? So that's what I'm going to do. That P1 V1 over N1 T1 equals P2 V2 over N2 T2. And that works because K equals K. But there's something different about this. Say, what do you mean there's something different about it? Well, I've got everything I could possibly change about a gas in that equation. So now K is worth figuring out because it's always the same. It doesn't matter how much you have. It doesn't matter what temperature. It doesn't matter what pressure. That K is always the same. So they stopped calling it K and start calling it R. So what you're looking at there is the ideal gas law. Now, normally it's written as a variation of this. P times V equals N times R times T, because that gets everything off the bottom. All I did is just multiply both sides by N and T. The fact is, it usually gets written as PV equals nRT. And then people try to say it out loud. PivNert. Okay. So if you talk to a chemist and you're talking about a problem and they say, "Ooh, it's got to do with gases," that must be a PivNert problem. That's exactly that's how they talk about it. It's PivNert. It should be Piv equals nert, but okay. So P stands for pressure times volume, V is volume, equals the number of moles, N, times R, which is the ideal gas constant. Times the temperature in Kelvin. Like I said, it's usually written PivNert. Okay, this time R doesn't depend on anything. It's really constant. So that means if I've got a set of conditions where I know the temperature, the pressure, the volume, and the number of moles, I can figure out R. Right? I know a place where I know the pressure, the temperature, volume, number. Hey, there is a place where we know all those things. At STP, 1 mole of gas is 22.42 liters. Right? So if I take my PV equals nRT and solve it for R, that R is going to be PV over NT. It's got to be capital T. And pressure, well, what's the pressure at STP? 1 atmosphere. Volume, what's the volume at STP? 22.42 liters. What's the number of moles? Well, that's 1 mole. And that temperature is, it was 273 K. Right? Because that's STP. 1 atmosphere, 0 degrees Celsius. 1 mole is 22.42 liters. I know all those numbers are true. So now I just have to divide them. Well, that's 22 point, I'm not typing the ones. 22.42 divided by 273. And I get 0.0821. That's 3 sig figs because it's 273. What units? Well, what cancels out? Nothing. So all of those units stay. Now, for some reason, they actually write it liter times atmosphere. They turn that around, but that's okay because multiplication is commutative. Mole Kelvin. So R has lots of units. They're a pain to write. Write them anyway. I do it every time. Because when you go to cancel out, if you put something in the wrong place, it won't cancel out. It needs all those units so everything cancels out. Right? So if you look it up someplace else, you'll see 0.08206 instead of 0.0821. Why do they do that? Because they did 273.15. And it's 208 there, so Does that make sense? They just got more sig figs. And Central Station. Yeah. Yeah. So, that's R. R is always 0.0821 liter atmosphere over mole Kelvin. It never changes. It's constant all the time. R never changes. R is always 62.4 millimeters of mercury over mole Kelvin. Oh, well, excuse me, Mr. Green. I was listening closely to what you just said. You said it was always 0.08201, and then you told me it was 62.4. How is it? Can it always be 0.0821 and still be 62.4? Check the units. They both have liters. They both have kelvins and moles. The difference is one has the pressure in atmosphere, the other one has it in millimeters of mercury. It would also be 62.4 liters torr over moles Kelvin. It would also be 8.31 liters kilopascals over moles and Kelvin. It's always the same number, it just has different units. So if you take 0.0821 and 1 atmosphere is 760 millimeters of mercury, you will get that. 760 times 0.0821 is 62.4. 101.3 times 0.0821 is 8.31. Those conversion factors for pressure. So they're all the same value, they just have different units of pressure. So, hey, that gives us a new way to count moles. By measuring temperature, pressure, and volume. I measure the temperature, the pressure, the volume, I can calculate the moles. Because up to this point, if I want to know moles of gas, I was restricted to STP. If it was a gas, I could measure its volume. And if it was the STP, I could do 22.42 liters for 1 mole. But now I can do N equals PV over RT. Just divide both sides by R and T. Okay. There's a huge difference between this equation and our first 4 equations. What's missing from this one that was in our first 4? I can think of 1 or 2 things. That would be the 1s and the 2s. There's no 1s and 2s in this. This doesn't tell me how it changes. This tells me what it is. I don't have a before and an after. So when you've been watching me write these things down and said, that's a pressure, that's a temperature, oh, that's a second temperature, it must be T2, the other one must have been T1. How come I just didn't call it T1 to begin with? Because there's not always 2 temperatures. If you're going to use this equation, you only have 1 temperature. Make sense? Yep. So if you've got a 2-liter bottle in this room, and maybe a little bit more than 19 degrees Celsius right now, but not much. How many moles of air are there? Hey, this would be number 9? Oh, 14. 14. Number 14 on your blue slip. I'm going slightly out of order, but that's okay. So I have 2 liters, that's a volume. 19 degrees Celsius, that's a temperature, and I know I'm going to make it 292 Kelvin. 74.7 millimeters of mercury is a pressure, and they want to know moles, that's N. Hey, does anybody know an equation with those four pieces in it? Bivnert. And I'm trying to solve for n, so I divide both sides by r and t. So I get n equals p. 747 millimeters of mercury times V, 2.0 liters, divided by R. I've got three numbers for R. Which one do I want to use here? Since my pressure is in millimeters of mercury, I want to use the one that has millimeters of mercury in it. So that was the 62.4 liters, millimeters of mercury over moles in Kelvin. And my temperature was 292 Kelvin. So I push the buttons. 747 times 2 divided by 62.4 divided by 292. There's two things on the bottom. You got to push divided twice. You push times, it's going to do the division first, then take that answer and multiply by what you get. And that's not what you want to do. Equals. Oh, and I got to do the. And I get 0.082, because that zero in front's not a sig fig. My two sig figs in my 2.0, and the zero in front doesn't count. What units? Well, kelvins cancel out down here. Liters cancel out here. Millimeters of mercury cancel out here. And I'm left with moles in the denominator of my denominator. And my algebra teacher taught me that the denominator of your denominator is your numerator, because you're going to invert it. So I get just moles as a unit, because 1 over 1/4 is 4. Yeah. Nope. Nope. You just have to be able to use them. Okay. So, extra super hard. That's not bad. So, it's got to be 15. What pressure is exerted by 1.8 grams of hydrogen gas in a 4.3 liter balloon at 27 degrees Celsius? So you got 1.8 grams, that's a mass. 4.3 liters of volume, 27 degrees Celsius is the temperature, and I know that's going to be 300 point K. And they want the pressure. Anybody know an equation with all those pieces in it? Well, the answer is no, you don't. Because we haven't put M in any equation. But what can I do with that mass? Well, I got grams of hydrogen. Grams of hydrogen I can turn into moles of hydrogen, right? So I have all the pieces I need to use Pivnert. That PV equals nRT. Got to divide both sides by V. So I get P equals nRT over V. And my 1.8 grams of H2, I want to get rid of grams of H2, change to moles of H2. 1 mole is 2.02 grams. So 1.8 divided by 2.02 is 0.89 moles of H2. So I can write that in, 0.89 moles of H2 times R. Which R? Doesn't matter. Just depends on what unit you want your pressure in. And since they didn't specify, I get to pick any one of them. I'm going to pick the actual metric one, which is 8.31 liters, kilopascals over mole Kelvin. The temperature was 300 K, 300 point K, and the volume was 4.3 liters. So I got that 0.89 still sitting in my calculator, so I just push times 8.31 times 300 divided by 4.3 equals, and with 2 sig figs, I got 520 because I had 516. And what units? Well, the moles cancel out, the kelvins cancel out, the liters cancel out, and all you're left with is kilopascals, which is good because you were looking for a pressure. Kilopascals is one of our units of pressure. It's okay? So, of course, we could solve for temperature, we could solve for volume. They just have to give us 3 of the 4 numbers. And the only variation is sometimes they give us moles and grams, and we can do that. Right? Okay. Let us talk about your density. Oh, density. No, density. Okay. The molar mass of a gas can be determined by the density of the gas. Think about it. The same volume has the same number of pieces. So if I had 22, if I was at STP and I had 22.4 liters, that mole of oxygen would weigh different than the mole of nitrogen. And I'd have moles, I'd have grams, and I'd have liters, so I can find density. So if they got different masses in the same volume, they'll have different densities in the same volume. And we all know density is mass divided by volume. Okay, now I'm going to give you another way of looking at molar mass. Molar mass is mass divided by moles. If it weighs 200 grams and I have 5 moles, 200 grams for 5 moles means each mole weighs 40 grams. 200 divided by 5. Right? So if I take the number of moles divided by if I take the number of grams and divide it by the number of moles, that'll tell me how many grams for each mole. That's what molar mass is, grams per mole. Okay? And I'm going to put those 2 equations together with N equals PV over RT. So all we're going to do is some substitution, so I get an equation that has density on one side and molar mass on the other. I should be able to just rearrange these. I mean, you can solve them each separately, then do one at a time, but you can actually put all these equations together. So, do some simple algebra. Okay, first, substitution. Since molar mass is mass over moles, then I can put this in place of moles. PV over RT. Everybody okay with that substitution? All I did was substitute for N. Okay. Now, we've got a fraction of the denominator. My math teacher never let me leave the fraction of the denominator. So I have to invert and multiply. So that's going to bring RT up to the top and leave PV at the bottom. And I'm also going to do a little bit of commutation too. I'm going to move them around. So I got mass times RT on the top, and I turned around the bottom. Instead of PV, it's got VP. But that's okay to do because multiplication is commutative. Why did I do all that trouble to move them around? Because look at this. I can substitute for M over V. Because M over V is density, right? So Molar mass is dRT over P. Density times R times T and P. So three things affect the density. The molar mass, how heavy each piece is, the temperature and the pressure. Warm air rises because when the temperature goes up, the molar mass has got to stay the same, so the density goes down. Less dense, it rises. That's why this equation explains why warm air rises and cold air sinks. When it gets cold, your temperature drops. The only way for that to stay the same is for the density to go up. And cold air sinks. Right. So that's why when there's a fire, you want to crawl along the ground, because the hot, nasty stuff's up there. The stuff you have a chance of breathing is still down there, because it's more dense. Yep. So, find the density of helium. At 25 degrees Celsius and 6.7 atmospheres. They want density. They gave me a temperature. And a pressure. The equation I know that has density, temperature, and pressure in it is molar mass equals dRT, let me write it again, dRT over P. And I'm tired of writing molar mass out, so I am just going to make molar mass a big script M. Okay. So how do I get density by itself? Well, I have to multiply both sides by pressure and divide both sides by R and T. So I end up with D equals P M over RT. I'll move the R and T. No, that RT's got to go. Oh, no, RT's on the bottom. Okay. I took the RT and moved to the other side. It's on the bottom. I took the P and moved to the other side. It's up top. Still works. Okay, so my pressure is 6.7 atmospheres. My molar mass. Well, it's helium. So that's a 4.00 grams. And you're going to keep the per mole here. Divided by R. I have to pick an R. The R I want to use is the one with atmospheres, which was 0.0821 liter atmosphere over mole Kelvin. And the temperature was 298 Kelvin. So I pushed those buttons. 6.7 times 4 divided by 0.0821 divided by 298 equals, with two sig figs, 1.1 and what units? Well, kelvins cancel, atmospheres cancel, moles cancel. So I'm left with grams on top and liters on the bottom. And it will always have units of grams per liter. Really hard? Okay. A gas has a density of 2.54 grams per liter at 25 degrees Celsius and 0.97 atmospheres. What is its molar mass? density, a temperature, which I know is 298 K, and a pressure, and they want molar mass. Anybody think of an equation that has those pieces in it? One we learned just a second ago. Molar mass equals dRT over P. And it's already set up for me. So the density was 2.54 grams per liter. Times R. I have to pick the R with atmospheres in it. So it's 0.0821 liter atmosphere over mole Kelvin times 298 K. Sorry, I went off the edge. Divided by 0.97 atmospheres. So it's 2.54 times 0.0821 times 298 divided by 0.97 equals. With two sig figs because the 0.97, that is 64. And what units? Well, my liters cancel out. My atmospheres cancel out. My kelvins cancel out. And I'm left with grams over moles, which is a molar mass. What could you use this for? Well, we know this isn't oxygen. Because if it's oxygen, my answer would have been 32. So from the density of a gas, it's a big help in identifying what gas it is. Fact is, this is where you get the number to go from empirical to molecular formula. You need a molar mass. This is one way of getting a molar mass. So if you got a gas, you tear it apart and figure out what its percentages are, and then you make that gas, then you find the density of that gas. You can you can help identify it really easily. Find its empirical and molecular formula. So we needed that grams per mole to go from empirical to molecular. This is one of the places they can get it. Make sense? So this is going to be our lab today. Our goal is going to be to find out a molar mass. So we're going to need a density, a temperature, and a pressure. Okay? To measure temperature and pressure, we can do pretty easily. We got gauges to do that. How do we measure density? Well, we measure the number of grams and the number of liters, and then divide. Everybody okay at that? So, first I'll pass out the instructions for the lab, and you'll read those while I'm passing out gas law practice number 3, because we'll go straight from here to the lab, and then you'll have your opportunity to work on both halves before you leave today. Does that make sense? The lab is really pretty quick. So take a couple minutes to read through that lab.